We did these drawings in class. We talked about how we are trying to get to 8. We even had like here we have a double bond down on this one, where electrons are being shared by both elements there. And you need to be careful and precise with your drawings, and really need to reference the periodic table. And this is one thing I wish I had done in class, so I'm going to pull up a periodic table here and talk about the easiest way to figure out valence electrons. So here we have a periodic table that it just shows the number of valence electrons. And it's real easy to just count across the periodic table, and I kind of imagine this 2 drags all the way across. So in my academic classes, I go 1, 2, 3, 4, 5, 6, 7, 8 to kind of help kids understand how many valence electrons. Now you all should know, when our nitrogen is right here, that nitrogen is 2s2, 2p3, which is why it has 5 valence electrons, because it's got the s2 and the p3. That's where the 5 comes from. But you can't constantly be going back, well, that's s2, that's p3, that's 3s2, 3p6. You can't constantly be doing that. That takes too much time. So just merely counting across the primary groups of the periodic table is the easiest method. This is also a real easy method for estimating how many bonds it's going to make. As you can see, the nitrogen is 3 elements away from being like a noble gas. So you can take a real quick estimate as to how many bonds. It may also help when you're dealing with, I don't know, let's say like sulfur here. Oop, you can't see that. Sulfur here. If you only have 1 element to bond to the sulfur, and sulfur's 2 electrons away, well, sulfur might need a double bond. There's only 1 element to bond to the sulfur, and it's 2 electrons away. It might need a double bond. So you can kind of use that also in your mind. I really like Lewis dot structures because it's a little bit of a puzzle. You're just trying to figure out how to put it all together. And if you hear that noise, that's my dog. So yeah, my dog's in the background going nuts. Exceptions to the octet. There are a bunch of exceptions to that rule of 8, and I spoke about this in class, that when you're looking at the periodic table, there are a chunk of elements in the corner here, and the corner starts with phosphorus right there, who often exceed 8 valence electrons when bonding. There's a couple of ways of explaining why they exceed 8. You might say they exceed 8 because they're 3s and 3p valence electrons, but their 3d valence electrons are empty. They're available empty space, so electrons can be shifted around into that space. You may also talk about electronegativity. In bonding, phosphorus is far weaker than, say, fluorine or oxygen. So it's not uncommon for fluorine and oxygen to kind of like yank the electrons around in weird ways because those 2 elements are so strong. So we see a lot of odd electron configurations with these elements, and it gets even more exotic as you get down to the bottom right there. Wow, that's the worst arrow I've drawn in the last couple of minutes. It's just getting worse. I'm sorry. As you can get really crazy as you move that direction. Then we looked at a bunch of really difficult lines, and we have this one here where iodine and fluorine are sharing electrons. That gets the fluorine to its 8, which is your primary goal, is to get the most electronegative element to 8. And then those weaker ones in the bottom right can exceed 8, and in this example, the iodine is, man, iodine has 5 pairs of electrons on it. So that's bonds in 2 directions. It's got bonds in 2, let's change to red so it's more obvious. It's got bonds in 2 directions, and it's got 3 extra pairs of electrons and that's going to help us figure out its shape. It's got bonds in two directions and three extra pairs. And what about this phosphate? Well, it's got a shared pair, a shared pair, a shared pair, and a double bond. So the double bond is still one direction between phosphorus and oxygen. So that's bonds in four directions, and there are no extra pairs of electrons on there. So what I'm also trying to do right now is prepare you for thinking about what the shape of the molecule is. So after we get all these dots drawn, we should also be thinking about what shape is this molecule. Let's kind of run through these others and we'll get back to that. There's a bonding pair, there's a bonding pair, there's a bonding pair, there's a bonding pair, and then here's a pair that's not shared, and there's a pair that's not shared. So that's got bonds going in four directions, and then it's got two. That's my attempt at a two. Let's try the eraser function here. Two extra pairs of electrons on the xenon. So it actually has electron pairs in 6 total areas there. Nitrate, I think I talked about how much I hate trying to draw nitrate. The reason I hate drawing nitrate is because the nitrogen is actually giving this oxygen at the bottom one of its electrons. So this red electron at the bottom came off of the nitrogen, and it's just really a pain to draw. It's not one that I come to easily. Probably one of the few though that is kind of funky to draw. E sulfite, we have a bonding pair, a bonding pair, a bonding pair, and then a non-bonding pair. So that one's got electrons in 3 directions and 1 extra pair. And that's an old school shape. That one's trigonal pyramid. You might remember that one from last year. We're going to go over that again in a minute. And the last one, bonding pair, unshared pair, unshared pair, unshared pair. And let's just point out again that we're still trying to get to the octet for those really strong electronegative elements, fluorine and oxygen, and the last two, we've gotten them up to 8. The xenon in F is way above 8. It is at, let's see, there's 5 pairs, so it's at 10 electrons. It has 2 bond directions and 3 extra pairs, so it has 5 electron pairs on it. It's got 10 valence electrons. That seems like a lot, but that's okay. We're allowed to. Because xenon is one of the weaker elements in terms of its abilities in bonding. Yes, it's a noble gas, but it's got a lot of electron shielding or shielding effect. So its electrons can be pulled around by some of the strongest elements on the periodic table. And I mean, it would have to be a strong element. You couldn't have xenon being pulled around by bromine. Bromine is not electronegative enough to really manipulate the electrons for xenon. Fluorine, however, is a very small atom with very little shielding effect, so its protons are going to have enough coulombic attraction to pull xenon's electrons into an odd configuration like we're seeing here. And then here is the line drawing version of it. But what's nice about the line drawing version of it, you can see some of those direction issues we were just discussing a lot easier. Like this one was just a hideous drawing on the previous page. But the way it's drawn now, you can really see that it has bonds in 4 directions and that there are 2 extra pairs of electrons on it. So I strongly suggest, as you're doing the any homework questions for your lab, that you just have a scrap piece of paper to kind of like try out a couple of versions. And if you're struggling with one, don't erase it. Try it again right beside it. Leave the evidence of your mistake behind so you can build upon it. Erasing your work is one of the worst things people do when they're studying and practicing. You really need to leave that there so you can look at it and go, oh, I see what I did wrong, and leave yourself clues to build upon and build upon and build upon and get better at what you're doing. We also talked about resonance and formal charge. Resonance is the idea that the electrons are not static, that they can shift around from element to element. And number 14, we are seeing an electron from this oxygen actually shift over to that oxygen and create this shape. We're not adding any new electrons to the mix, we're just moving them around. And then at 15, that this is a -1 charge here on thiocyanate. That's a polyatomic ion called thiocyanate, and it's not uncommon in our world as we move forward here in AP chemistry. And that one giant red electron I have shifting from the sulfur to the nitrogen, and because it shifted, it changes the number of bonds on each of those elements. And then the last thing was odd electron model. If you add up all of the electrons on your elements and you end up with an odd number, this is going to be an odd drawing. It is very difficult to satisfy the octet rule when you don't have enough electrons. Honestly, I imagine that this molecule, NO, often steals electrons from others, but that's not the case. We have occasionally found nitrogen monoxide that will be semi-stable. And what's happening is the electrons are jumping back and forth between the nitrogen and the oxygen so that one element is stable and then the other element is stable. But kind of the whole purpose of this page with the resonance structures is that there can be multiple correct answers. As long as you're satisfying the octet rule and trying to build everything correctly, you should have a correct answer. But it's going to take time and practice for some of those more complex molecules. All right, let's hit formal charge now. Formal charge is when you calculate basically what the charge is on each of the elements involved in bonding, and you look at the normal number of valence electrons compared to the valence electrons that are actually being assigned to that atom, and you just write down the charge. In this example, you can see I circled the elements to kind of count how many electrons were assigned to it. And by assigned, we mean, well, what if that bond was cut in half right there? And so that's why I drew those circles to kind of imagine it was cut in half. And the chlorine on the top and the left would both have 7 once you cut that bond in half. And that's the normal valence electrons for chlorine, so that's why the charge of 0 is written in purple. Same thing for the chlorine at the bottom. Where it gets interesting is the phosphorus in the middle. When you cut those bonds in half, the phosphorus only has 4 valence electrons. Well, phosphorus is supposed to have 5. If it only has 4, it's lost 1. So the formal charge for phosphorus is a +1 because it lost 1 of its electrons. And conversely, the oxygen has 7 valence electrons when you cut that bond in half, which means it has 1 extra valence electron in its formal charge. Formal charge, I don't know why I changed tones when I say formal charge. Its formal charge is a -1. I don't think I had all of these different shapes drawn when you guys were taking the notes. You might want to pause the video now and just kind of close your laptop and try these 4 on your paper. Don't cheat, don't look at them. Oh, I see you looking right now. All right. Well, if you didn't pause, I'm going to go ahead and explain what's going on here. We have a lot of violations of the octet rule going on. So A and B I did in class, but C, we have the bromine, which has 7 of its valence electrons, and I'm just trying to put a little dots there to represent the starting ones before they bonded. And they're bonding to fluorine. Well, fluorine has to get to 8. Fluorine is the most electronegative element on the periodic table. It will definitely get to 8. It will pull electrons from any weaker element to get to that 8. And so the fluorine in this molecule is making a bond to the bromine. There's 3 of them. Well, that's going to take the bromine from 7 valence electrons. When it makes the 3 bonds, it's going to have 10 electrons around it. And you can see it's got these 2 pairs up at the top, and then it's got the 3 bonds. So it definitely has the number of electrons we're just talking about there. what's weird is that shape. We don't know that shape yet. We're going to go over the odd shapes in a minute. But look, that's got bonds in 3 directions. And then on the top of the bromine, there's 2 extra pairs of electrons. You see the same exact thing going on with this molecule down here. It's not really a coincidence because iodine and bromine are both those large halogens. Fluorine and chlorine are smaller halogens, and they can often pull the electrons around. And then we have that xenon tetraoxide where oxygen is either, and I've got 2 different answers sitting here. Here in this drawing, the oxygen is actually pulling electrons off, and you see these purple dots on the outside. Some of those are electrons being pulled off the xenon to get the oxygen to 7. And then once it's at 7, it only needs a single bond to the xenon. And in the other drawing, I did not pull them all. I made some double bonds instead. And both of these drawings are accurate. They are resonance structures. Notice that each drawing, you have bonds in 4 directions and 0 extra electrons on the xenon. Again, the xenon is going in 4 directions to each oxygen, and there's 0 extra. Hey Murph, whoa, whoa, whoa. That's a double bond there. How do I deal with that? Well, the double bond is just one direction. It's a direction, it's counted as one direction from the xenon to the oxygen. There is some interesting bond order stuff going on in there, which we are going to get to a bit later. And then the last one, that phosphorus with 4 fluorines and then a +1 charge. That means you get to remove one of the electrons. As you draw this one, go ahead and make your single bonds from fluorine to phosphorus, and then the phosphorus has 1 electron that's just hanging out and doesn't know what to do. That's the one you need to erase. You erase that one to get it the +1 charge achieved, and then everything's balanced out. Alright, here is the VSEPR geometry sheet that's in your notes. That's valence shell electron pair repulsion. Again, valence shell electron pair repulsion. So pairs of electrons repel other pairs of electrons to create these shapes. And they always maximize the distance between the shapes. You do need to know the angles of every single thing up here. Oh my goodness, lots of angles. And most of them have a base angle that can kind of be seen in this column right here. If you look at this column and then you start to work your way across, you see the same angles again and again and again. In fact, let's kind of point out that this is the most important column. It's the base geometry, and that base geometry is repeated as you go to the right. But as you go to the right, instead of having all bonds, like this one here is bonds, 5 bonds. Now it's 4 bonds and a pair of electrons. Now it's 3 bonds and 2 pairs of electrons. 2 bonds, 3 pairs of electrons. So as you go across this chart, the number of bonds is replaced by extra pairs of electrons. So if you look, I have written all over the chart. You want to maybe pause it in a second and write all this down. I've written 2 directions, 0 extra, 3 directions, 0 extra, 2 directions, 1 extra, 3, 4, 3, 3. You want to go ahead, pause this video, and write that down. And I'm going to just pause my voice where you're supposed to pause the video. Here we go. Also, you might notice that I wrote whatever the heck this is. Go ahead and jot that down. That's called hybridization. I'm going to be going over that later in the video, but I'm not going to come back to this page. But the hybridization works for every element that way, or for every element that way. So as you move left to right, everything in there is the same type of hybridization. And we're going over hybridization kind of at the end of these notes. So let's just draw one of those ones we had a minute ago. We had, what did we have? We had iodine and 3 fluorines. That's the one we just had. And the iodine and 3 fluorines had 3 single bonds, and then a pair of electrons, and another pair of electrons, and then of course the fluorines had their others. But you have to draw these other electrons just to get the fluorine to their octet, but that's not really impacting this decision we're about to go through. So we have the iodine has 3 bond directions, and then it has 2 extra pairs, and then you kind of have to go through a mental checklist. Well, that's bonds in, we have 5 electron domains. 2 plus 3 is 5 electron domains. And, well, that's not all 5, so it's not this shape. No, that is not going to be this shape because that's 4 bonds. No, it's going to be this shape here. It's called T-shaped. And when you get to the lab a little bit later and you build that, I want you to take specific note of why might this be named T-shaped. When you build the models, you will see that these elements here, or the bonds, are actually kind of forming a T letter shape. That's why it's called T-shaped, based off of the shape of the bonds. And then the one that a lot of people struggle with is this sawhorse or seesaw. I usually say seesaw. And that one is because the bonds are making, there's 2 bonds and then there's 2 bonds this way with this atom in the middle, and they're kind of making a seesaw shape. If you've ever been on a seesaw, you know what I'm talking about. But take a look, you have all these different names. You have octahedral, square pyramid, square planar, T-shaped again. So let's actually highlight that at T-shaped, and that's T-shaped. And then here we have linear, linear, and linear. And all 3 of those linears mean that the elements that are bonded to the element in the middle make a straight line. But the difference with these 2 is they do have extra pairs of electrons on them, but the primary bonds form a straight line. The bonds form a straight line. Okay, so you're going to have to spend some time getting to know this graph, building models, and taking a look at it. Hybridization. So what the heck is hybridization? Hybridization is when the orbitals, the S and P orbitals kind of blend together to make new orbitals. And because they're blending together, we call them hybrid orbitals. Hybrid means to mix or fuse together, and that's what's going on here. So if you are mixing a S orbital and 3 of the P orbitals together, you make 4 sp3 orbitals. That was very poorly written. Try that again. sp3 orbitals. And those sp3 orbitals all look identical as the S and the 3 P's merge together, and this allows an element to have bonds in 1, 2, 3, 4 directions. And this is our basic tetrahedral shape. So this is bonds in 4 directions. It could also be bonds in 3 directions and 1 extra pair. That's the trigonal pyramid, where you maybe have a pair of electrons here instead. Or it could be bonds in 2 directions and 2 extra pairs. So maybe I'll put a pair of electrons here. And that one we normally call bent. This one we usually call bent. This one we usually call trigonal pyramid. And that one we usually call tetrahedral. But all 3 of these names have electrons in 4 directions. And it's either pair of electrons, bond, bond, or all of them are bonds. But that hybridization occurs anytime that four-direction shape is achieved. The valence electrons are getting pulled around by the other elements' nuclear charge and blending the orbitals together. And that blending of orbitals is again called hybridizing orbitals. So we have sp3 hybridizing orbitals. That's when an s and 3p orbitals bond. This particular page is talking about sp2 hybridizing, and that's when one of the s's and two of the p's. And oh, I forgot to remind you that sp3 means there's 4 electron pairs around it. sp2 means there are 3 electron pairs around it. This would be like your trigonal planar. And then there is also, of course, going to be sp, and that is going to be 2 electron pairs. And I like to point out that if you just add these, oops, that's not going to show up. If you add these superscripts together, 1 plus 3 equals 4 directions, 1 plus 2 equals 3 directions, 1 plus 1 equals 2 directions. You can easily take the number of bonds and figure out the hybridization. You just start off by writing down, okay, it's going to have use an S and it's going to use a P. How many directions? Let's see, this one's going in 1, 2, 3 directions. Oh, there's no extra pairs. That's going to be sp2. The hybridization is easy to figure out, and really you're just talking about orbitals blending together, and this name is telling you how many orbitals blended together, an s orbital and 2p orbitals. Here's one more of the same idea, that the s orbital and the p orbital are blending together to make sp orbitals. This would be like if you had beryllium chloride, the beryllium atom is making a single bond to each of the chlorine atoms, and it has bonds going in 2 directions. There's no extra electrons. This would be the linear shape. And then where does this sp come from? Well, beryllium is 2s2, 2p0, but once it bonds, one of these electrons is promoted into that space, and it becomes 2s1, 2p1, and then they blend together to make an sp orbitals. They make 2 sp orbitals, and this space here is called an sp, and this is an sp. I was slightly wrong there at the end. The electrons around beryllium get pulled into these 2 new orbital shapes called sp orbital shapes. So again, when you have bonding in 2 directions, it is sp. If you have bonding or electrons in 3 directions, it's sp2. And if you have bonding in 3 directions, it's sp3. Now you might have noticed on that chart earlier that I had these written in one color, these written in a different color. And that's because the hybridization for the large ones, trigonal bipyramidal and the octahedral shapes, are actually not very well known right now. There's some debate among physical chemists as to whether or not those hybridizations exist. And because that's under debate, we don't actually test that. So some of those things appear on your lab, but it clearly says on your lab that those are not being tested. And then here's some more drawings of the different SP shapes. And you should probably practice, more practice. And lastly, bond energies. When 2 bonds form, let's do, this is definitely one of my favorite molecules to draw, C2H4. So you have the 2 carbons, and you have 4 hydrogens, And the easy part of this is that bonds form between the hydrogens and the carbons, and those electrons are shared, shared, and shared. And then of course you also have electrons that are being shared between two carbons. But there is one more set of bonds, and well, let's pause here for a second. Right now we have hydrogen, hydrogen, carbon, and the quick drawing is going to look like this. The quick drawing, after I would all be done, would look kind of like that. And you can see the carbons are going in 3 directions. Double bond counts as one direction, and there's 0 extra pairs. So this is sp2 hybridization. This is a trigonal planar shape, molecular shape. But what happens to that other electron? There's one more electron on both of these carbons, and a double bond needs to form. Well, this electron is actually not in one of these sp3 orbitals. It's in a p orbital all by itself. And that p orbital would be on the y-axis, and the electron can actually jump from this orbital to that orbital and back and forth. And this electron can jump back and forth. And so when this double bond forms, a unique type of bonding exists, which is slightly different energy than a single bond. So the single bond is called a sigma bond in terms of its energy. And sigma bonds are pretty strong because they're a direct connection between the two elements. The pi bond is a second bond. The pi bond occurs between the p orbital and the other p orbital. And the bond actually forms because these two orbitals blend together. They can't go through this space in the middle because that space is already occupied by 2 electrons. And as we know by the Pauli exclusion principle, you can only have 2 electrons inside an orbital. So the pi bond is the second bond that forms. So the sigma bond is the first bond. Wow, that is really hard to read. The sigma bond is the first bond. A pi bond is when you have a double bond. Oh, what if you have a triple bond? That would be another pi bond. If you have a triple bond, you have a second pi bond. But the first bond that forms is always called a sigma. The second one is a pi bond. The third one is a pi bond. And to be clear, I mean between 2 elements, like say carbon to carbon. If you had a triple bond between 2 carbons, then the first one would be the sigma, and the other 2 would be pi bonds. And pi bonds are lesser energy, but you are adding all of that energy together. So you have the really strong energy of the sigma bond, plus the weaker energy of the pi bond, plus additional energy from the triple bond. Whew, we're almost done. Almost done. There's only 2 more. Why am I wasting time saying almost done? So here we have a picture of carbon dioxide, and we have a pi. Wait. Start over. We have the sigma bond. We should talk about that first. We have the sigma bond that forms first between the carbon and the oxygen. There's a sigma bond on the left and a sigma bond on the right. That's the first of the bonds. And then after that, we have the second bond, and that's the pi bond. And the pi bond is forming between the p orbitals there. That's one of the pi bonds. And then down here, that's the other pi bond. And so with the carbon dioxide, that's a tiny, tiny carbon dioxide. You have the single bond and the single bond to the oxygens. Those were sigma bonds. And then we have a pi bond and a pi bond to the second one. That pi bond got a little off balance there, didn't it? And then the same thing's going in the last one. You see that there's a triple bond between the 2 carbons. And so the first of the bonds is the sigma. Then we have a pi bond and a pi bond. And so the sigma bond has a lot of energy. And we're adding a little bit more energy with the pi. We're adding a little bit more energy with the pi. So breaking those 2 carbons apart is going to take more energy than if we just had a single bond between 2 carbons. because a single bond would just be one bond holding it together, which is a pretty strong bond, but the triple bond has additional and even more energy associated with it. Alright, this is the last slide. Now what you need to do is grab the lab and start drawing Lewis dot structures, trying to build the models and working your way through it. You should also be picking up some homework. The answers to the homework are posted on my Google page, on the running calendar we have at Google. Good luck, everybody, and have a great homecoming weekend.